Okay, let's talk about Keras and how it stacks up against TensorFlow. Think of TensorFlow as the powerful engine underneath it handles all the complex math and operations. Keras is like a really helpful dashboard that sits on top of that engine. It makes building those networks much easier. It's designed to be quick and intuitive, letting you experiment with different ideas without getting bogged down in the details. Essentially, TensorFlow provides the foundational tools, while Keras gives you a simpler way to use them effectively. They work together really well, and Keras is now deeply integrated into TensorFlow. Okay, so let's talk about why Keras is such a fantastic choice for your deep learning projects. Basically, it's all about speed and ease of use. You can really jump in and start building models super quickly. You don't have to spend ages wrestling with the lower level parts. It has a really user-friendly interface, letting you define your model using simple sequences or functional API, so you can focus on what asterisk matters asterisk, getting good results. Plus, Keras is super flexible. It works well with TensorFlow and lets you add in your own custom components. And don't worry about getting stuck. There's a huge community and lots of helpful resources available to guide you. Okay, so when talking about Keras, it's really important to understand its core parts. First up, we have models. Think of them as the blueprints for your neural network. Then there are layers, which are the individual building blocks like convolutional and dense layers that do all the heavy lifting. Next, you've got optimizers. These guys control how your model learns by tweaking those weights to minimize errors. Loss functions measure how well your model is doing. Basically, they quantify the difference between what it predicts and what's actually happening. And lastly, but not least important, we have data handling. Keras works really well with TensorFlow's data tools, so you can efficiently feed your data into the network and even use techniques like data augmentation to make it more robust. Okay, let's talk about defining a sequential model in Keras. It's really straightforward. A sequential model is essentially a chain of layers stacked on top of each other. It's the most basic type of Keras model and perfect for building simple neural networks where data flows linearly from one layer to the next. You create one using Keras models sequential. Then, you add your layers like dense or convolutional layers to this chain using the add method or by directly listing them in the constructor, as we see here with an example that creates a model suitable for processing images from MNIST. Okay, let's talk about how Keras handles building neural networks. The sequential API is the easiest way to do it. You just stack layers one after another, like building with Lego bricks. It's great for simple models where everything flows in a straight line. Now the functional API gives you much more control. Instead of a single chain, you define your model as a whole graph, allowing layers to connect in different ways and handle multiple inputs or outputs. It's more flexible but also slightly more complex. Understanding these differences is crucial for designing effective models. Okay, so let's talk about compiling your Keras model. Think of it as setting the stage for training. You're telling Keras how you want it to learn. The most important things to configure are the optimizer, which decides how the model adjusts its weights during training, the loss function, which measures how wrong your predictions are, and metrics like accuracy that help you track progress. You can also tweak the learning rate, but be careful with that one. A good starting point is model, compile, and it's pretty straightforward to see those parameters in action. Okay, let's talk about model fit. Think of it as the engine that trains your Keras model. It takes your already built neural network and feeds it data, both what you're showing it the inputs and what you want it to predict the labels. Then, using an optimization algorithm like ADAM or SGD, it tweaks the model's internal settings until it gets really good at making accurate predictions. You control how many times this process happens with something called epochs, and how much data is processed each time with batch size. It's a fundamental step in turning your model into something useful. Okay, so when it comes to evaluating your Keras models, don't just look at that shiny accuracy number. It's really important to set up your data properly. Splitting it into training, validation, and test sets is key. Then pick the right metrics for what you're trying to achieve, whether you're doing classification or regression. Things like precision, recall, and phone score are useful for classification, while MSE and RMSE are great for regression. Cross-validation helps give you a more reliable picture of how your model will perform in the real world. And don't forget about tools like confusion matrices to pinpoint where your model is struggling. Learning curves can also be super helpful. They show you if your model is overfitting or underfitting. Okay, let's talk about model predict. This is how you actually use your trained Keras model to get predictions on new data. Basically, you feed in some information, usually a NumPy array or a TensorFlow tensor representing the input, and it spits out the model's output, which are its predictions for that specific input. It's like asking your model, what do you think this will be? The example shows how easy it is to load a trained model and then just use predict with some sample data to get those predictions. Okay, so when you've spent a lot of time training your Keras model and it's performing really well, you'll want to be able to use it again without starting from scratch. That's where saving and loading comes in. The easy way to do this is with the model save method. Just call that on your trained model and specify a file name. It will save the entire thing as an HDF5 file, which is pretty standard. Then to load it back up later, you use Keras models load model, giving it the path to the save file. It's really that simple. Just make sure the directory structure matches where you saved your model originally. Okay, let's talk about callbacks in Keras. They're like little helpers you can add to your training process. Basically, they're functions that run at specific points, like when a batch is complete or when validation loss changes. Why do we need them? Well, they give us a ton of control and allow us to monitor our model's progress in really detailed ways. For example, you might want to stop training early if the model isn't improving on a validation set. That's where early stopping comes in handy. Or perhaps you want to save the best version of your model as it trains. Model checkpoint does exactly that. Then there's reduce LR on plateau, which helps our optimizer avoid getting stuck by reducing learning rates when things stagnate, and TensorBoard lets us visualize everything happening during training. Let's talk about early stopping, a really smart way to keep your Keras models from getting bogged down in overfitting. Basically, it watches how well your model performs on unseen data, the validation set, while training. If the validation loss starts increasing, meaning the model is learning noise instead of patterns, early stopping kicks in and stops the training process automatically. This saves you a lot of time and resources. You define what metric to monitor, often its validation loss or accuracy, and how many epochs without improvement patience before stopping. Then, we add an early stopping callback to our model, telling it to watch those metrics and stop when necessary. Okay, let's talk about learning rate schedulers. Think of your model's learning process like trying to find the bottom of a valley. You don't want to overshoot and bounce around wildly. A fixed learning rate can be problematic for that. So, what's a learning rate scheduler? It's essentially a way to dynamically adjust how quickly your model learns as it trains. Instead of using the same learning rate throughout, we change it based on things like how many epochs you've gone through or even the value of your loss. Schedulers can help your model converge faster and more reliably by making those adjustments. Keras provides a few built-in options like decreasing the learning rate in steps, decaying it over time, or adapting it to the gradient size. You pass the scheduler as a callback during compilation, and you'll see improvements in training speed and stability. Let's talk about customizing loss functions in Keras. It's a really powerful feature. You don't always have to stick with the built-in options like categorical cross-entropy. Basically, you can create your own loss function that's perfectly suited for your specific problem. There are a few ways to do this. You can subclass the TF Keras loss class, which gives you full control over initialization and calculation, or you can use lambda functions. These are great for simple losses where you just want a quick way to calculate the error. And finally, if you need really fine-grained control, you can directly use TensorFlow operations within your loss function. The important thing is that your custom loss needs to take predicted and true values as inputs and return a single number representing how good or bad the model's prediction was. Okay, let's talk about how you'd build a custom metric in Keras. It essentially involves creating a class that extends Keras metric. You start by initializing it. Setting its name is really important for tracking during training and logging. Then we implement an update step method. This gets called after each batch of predictions, receiving the true labels and what your model predicted. Inside this function, you update your metric's internal state, like summing up differences between the two. It's a good idea to have a reset method to think of it as clearing the slate before starting a new epoch. Finally, there's a getValue method which aggregates all the updates and returns the final calculated value that you can then use for evaluation. Okay, let's talk about sigmoid and softrax. They are both activation functions, but they do different jobs. Sigmoid squeezes any input into a range between 0 and 1. Think of it as giving you the probability of something happening. It's great for binary problems like is this spam. Softmax is where things get more interesting. It takes a bunch of numbers and turns them into a whole set of probabilities that add up to 1, representing different classes. So, if you're classifying images cat, dog, bird, softmax is your go-to. The key difference is sigmoid gives you a single probability score, while softmax creates a complete probability distribution for all the possible outcomes. Okay, let's talk about batch normalization. It's a really important concept when building Keras models. Basically, it helps make training much more stable and faster. What it does is take the outputs of each layer in a mini batch, calculate their average and standard deviation, and then normalize those values. It then adjusts them slightly using learnable parameters. Think of them as scaling and shifting knobs so they can adapt to the data. Because this process reduces the internal covariate shift where the distribution of activations changes during training, you can often use higher learning rates, and it generally leads to a more robust model that trains faster. Okay, let's talk about dropout, a really important technique for preventing your Keras models from memorizing the training data and becoming overly sensitive to noise. Essentially, it's like temporarily shutting off some of your neurons during each training step. This forces the network to learn more generalized features, making it perform better on unseen data. You can add dropout directly into your sequential or functional API models using the dropout layer. Just specify a rate, which controls how many neurons are dropped out, usually between 0 and 1. A higher rate means more neurons get turned off. You can also choose an activation function to use on those dropped neurons, and remember it's only active during training. You don't want dropout when you're making predictions. Okay, let's dive into a really important concept in CNN, padding. Think of it like this: when you're using convolutional layers, the size of your feature map shrinks as you go deeper into the network. If you don't do anything about it, information at the edges of your images gets lost. Padding is how we combat that. It adds a layer of zeros around the input image borders. This ensures that the convolutional layer still sees all those edge pixels and helps maintain spatial relationships. There are different ways to pad: valid, which means no padding; same, which keeps the output size the same as the input; and full, which pads everything out, giving you a bigger feature map. It's all about controlling what information gets preserved during your network's processing. Okay, let's talk about transfer learning in Keras. It's a really powerful technique. Basically, instead of training a neural network from scratch, we use a model that's already been trained on a huge dataset like ImageNet. This saves us tons of time and often leads to better results because the pre-trained model has learned general features. You load this model using TF Keras applications. Just pick your favorite architecture. Then, you modify the output layer to match what you're trying to predict with your new data. Often, you'll start by freezing all the layers of the pre-trained model so it doesn't change drastically during initial training. You train only on your specific dataset, and then, if needed, you can unfreeze some layers towards the end for fine-tuning. Okay, let's talk about freezing and unfreezing layers in Keras, a really important technique for getting the most out of your models. Basically, you can tell Keras which parts of your network to train and which parts to keep as is. When you freeze a layer, its weights are locked down, it won't change during training. This is super useful when you're doing transfer learning, like taking a massive image recognition model that's already been trained on millions of images and adapting it to your specific task. You might freeze the initial convolutional layers and only train a few new ones at the end, which saves a lot of time and resources. You can do this by setting layer trainable equals false. And if you want to start training those previously frozen layers, just set layer trainable equals true. It's all about strategically controlling what gets updated during backpropagation. Okay, let's talk about optimizers and Keras. They're crucial for training your models. There are a few common ones. Atom is probably the most popular. It intelligently adjusts learning rates for each parameter. Then you have SGD, which is really simple but can be tricky to tune. RMSprop adapts learning rates based on how much noise there is in the gradients, and Momentum helps smooth out the training process by adding inertia. Basically, they all work differently to find the best weights for your model. Okay, let's talk about visualizing your Keras models. It's really important to get a good sense of how they're structured and what each layer is doing. When you use the sequential API, it's pretty straightforward. You can just see the layers in order. But with the functional API, things get a bit more complex because your model might be built from multiple interconnected modules. That's where TF Keras Utils plot model comes in handy. This function lets you create images or interactive graphs of your model's architecture. You can customize how it looks, showing layer shapes and module names, for example. It's a great tool to help understand the flow of data through your network and catch any potential issues early on. Okay, so let's talk about imbalanced datasets. They are super common in real-world machine learning. If one class has way more examples than another, your model can easily become biased towards the majority class. To combat this, we have a few good strategies. First, you can try data resampling techniques. Oversampling creates synthetic data points for the minority class, like using SMOT. Undersampling randomly removes some examples from the majority class. Then there's cost-sensitive learning, essentially telling your model that getting those misclassifications of the minority class is really important by adjusting the loss function's weights. Finally, ensemble methods can be powerful. Think of combining multiple models trained on slightly different versions of your data. It's really important to remember to test thoroughly with a held-out dataset to make sure you've actually improved things. Okay, let's talk about data augmentation. It's a really important technique in machine learning, especially when you don't have tons of labeled images. Essentially, it's like making new versions of your existing training pictures, rotating them slightly, zooming in or out, flipping them horizontally, all without actually collecting more original photos. This helps your model learn to recognize patterns even with variations in the data, improving its ability to generalize and avoid overfitting. We use image data generator in Keras, which applies these transformations during training on the fly. There are lots of different techniques you can apply: rotations, zooms, shifts, flips. It really depends on your specific data set and what kinds of variations you want the model to see. Okay, let's talk about image data generator. It's a fantastic way to boost the performance of your image models. Basically, it's like a built-in photo editor that generates variations of your training images automatically. This is super helpful because it helps prevent overfitting and makes your model more adaptable to slightly different image styles or lighting conditions. It works by creating new batches of images with small random changes, think slight rotations, shifts in position, zooms, or shears. You control exactly how much these adjustments are using parameters like rotation range and shift range. The beauty is that it does all this on the fly as you train, so your model sees a wider variety of data. Okay, let's talk about something really important when training deep learning models. It's called model checkpointing. Imagine you're baking a cake, and after one step, the batter suddenly tastes terrible. You wouldn't just keep adding more ingredients, right? You'd go back to the previous good batch and try again. Model checkpointing is similar. It's a way of saving your model's progress so that if things start going wrong during training, you can easily revert to a working version instead of having to start completely over. Keras provides a handy callback called model checkpoint that does all the heavy lifting for you. It automatically saves the model's weights at regular intervals or whenever it sees an improvement in your validation accuracy, making it super useful for experimenting with different settings and ensuring you always have the best performing model. Okay, let's talk about how to handle multi-class classification in Keras. The basic strategy involves using dense layers, think fully connected networks, and ending with a softmax activation function. This ensures that the outputs represent probabilities for each possible class and add up to 1. We'll typically use ReLU activation in our hidden layers, which is a good default choice. When compiling your model, it's really important to select categorical cross-entropy as your loss function. This is specifically designed for one-hot encoded labels. And remember, you need to make sure your target labels are converted into the correct format using one-hot encoding. Okay, so let's talk about loss functions in Keras. We often use them when training multi-class classification models. There are two main ones you'll encounter: categorical cross-entropy and sparse categorical cross-entropy. Categorical cross-entropy needs one-hot encoded labels. Basically, each class gets its own vector where only the correct class has a 1, everything else is 0. Think of it like this: if you have 3 classes, cat, dog, and bird, the label for dog would look like 0, 1, 0. Sparse categorical cross-entropy, on the other hand, takes integer encoded labels, just the class index itself. So, instead of a vector, you give it the number representing the correct class. It's simpler and often more efficient when your labels are already in this format. The main difference is how they interpret those target values. Okay, let's talk about multi-label classification in Keras. Basically, this is when a single piece of data can belong to multiple categories at once. Think of classifying images with multiple objects or documents discussing several topics simultaneously. The key here is how we set up our output layer. Instead of using a softmax activation, which is for multi-class problems, we'll use a sigmoid activation function on each individual neuron in the final layer. Each neuron represents one label and will output a probability between 0 and 1, indicating how likely the label is present. Keras handles the binary classification part for each label independently. The code snippet shows you how to set up your model with this approach. Just make sure your number of labels matches the size of the final dense layer. Okay, so let's talk about dealing with gaps in your data before feeding it into Keras. It's really important because a model can't learn from nothing. First, you need to figure out exactly where the missing values are and why they're there. Is it random, or does something else explain them? Then, you have a few options. You could just throw away rows with missing data, but that loses information. Or, you might use methods like replacing those missing numbers with the average of all the other numbers in that column, or perhaps using the most common value. More advanced techniques include finding similar data points to fill them in, or even building a whole new model just to predict what's missing. Finally, sometimes it's helpful to create an entirely new feature that tells you if a value was missing. This can actually give your model some extra insight. Okay, let's talk about how Keras handles validation during training. Both validation split and validation data are important, but they work a little differently. Think of validation split as a simple way to reserve a percentage like 20% of your data for checking out how your model is doing. It's easy to set up. But if you need more control or want to use completely separate datasets for training and validation, then validation data is the better choice. With validation data, you actually provide a pair of the data you'll use for training and the corresponding labels, along with the data you'll use for validating. So, it gives you more flexibility to tailor your validation process. Let's talk about some important things to keep in mind when using Keras. It's a brilliant tool for quickly getting deep learning models up and running, but it does have limitations. Primarily, Keras hides a lot of the underlying details from you. This can make debugging more difficult if something goes wrong. It also relies on a backend like TensorFlow, so performance and specific features might vary depending on what you're using. While it's great for prototyping, if you're doing really advanced research or need extremely fine-grained control over your model, you might find that TensorFlow's lower-level API gives you more freedom. So, understanding these limits is just as important as knowing how to use Keras effectively. Okay, let's talk about creating custom layers in Keras. It's a really powerful technique for making your models more flexible and reusable. The first thing you do is subclass Keras layers layer. Then, you need to set up the initialization with an init method where you can define any parameters or state your layer will have. Next, you'll override the build method. This is called when the layer receives its inputs and is the perfect place to create the weights and biases for your layer. Don't forget to call super, build and put shape at the end. Finally, define how the layer transforms its input in a call method. That's where you perform the actual computation using your defined weights and biases. Okay, let's dive into the functional API in Keras. It's all about handling complexity when you're building models that aren't just a simple sequence of layers. Imagine you're working with a really sophisticated model, maybe one that combines image recognition with natural language processing. The traditional sequential approach can get messy fast. The functional API lets you build your model as a flexible graph, making it much easier to manage multiple inputs and outputs, reuse components, and generally keep things organized when your architecture gets more elaborate. Let's talk about how we can introduce attention into our Keras models. Attention is incredibly useful, especially when dealing with sequences, things like text or time series data. Essentially, it helps the model figure out which parts of the input are most important for generating each part of the output. There are a few ways to do this in Keras. One common approach is dot product attention, where we simply calculate the similarity between the query and key vectors. Another method is additive attention, often seen in encoder-decoder setups. Finally, scale.product attention, which is fundamental to the transformer architecture, involves scaling the similarities scores, a technique that can help with training stability. Okay, let's talk about how we train our Keras models. Often, you'll encounter the fit and train on batch methods. Think of fit as a more complete solution. It takes care of compiling your model ***, then running through multiple batches to actually learn. It's great for typical training scenarios where you want a full iterative process. Now, train on batch is more focused. It's designed to train just one batch at a time. You need to compile the model separately before using this method. The key takeaway is that fit handles everything in a single call, while train on batch requires you to manage the compilation steps yourself. Okay, let's talk about learning rate warm-ups in Keras. They're really important for getting stable training, especially if you're using optimizers like Adam or RMSprop. The idea is that during the very first few epochs, your model's gradients can be pretty noisy and erratic. It's a bit like starting a car cold. A warm-up period gradually increases the learning rate, allowing the model to settle down and get a better handle on the training process before you ramp up the full speed. We use Keras callbacks for this. Essentially, we define a schedule function that dynamically changes the learning rate based on the current epoch number. You can adjust the number of warm-up epochs and how much you scale the initial learning rate. It's all about finding what works best for your specific model and dataset. Okay, so you've built an awesome Keras model. Congratulations. Now comes the real challenge, getting it into action. There are several ways to do this, really. A popular approach is building a REST API using frameworks like Flask or Fast API. Think of it as creating a little website that your application can talk to and ask for predictions. Another option is Docker, which packages everything your model, the code that uses it, and all its dependencies into a self-contained unit, making sure it runs consistently everywhere. Serverless functions like AWS Lambda or Google Cloud Functions are great if you don't need constant uptime. They only run when needed, keeping costs down. Finally, specialized model serving platforms like TensorFlow Serving or Torch Serve are designed specifically for this task and handle things like scaling up as demand grows. Okay, let's talk about how Keras speeds things up with GPU. Basically, Keras is a wrapper around other deep learning frameworks like TensorFlow. When you define your model in Keras, it uses the backend's ability to calculate gradients automatically. That's crucial for training. If you have a compatible GPU installed and the drivers are set up correctly, Keras will intelligently move those calculations onto the GPU, which is much faster than using your CPU. You can even tell Keras exactly where to run specific parts of your model using the toGPU method or by specifying the device type within a layer. It's all about leveraging the power of these dedicated graphics cards. Okay, let's talk about evaluating and predicting with Keras generators. There are two key methods you'll want to know: evaluate generator and predict generator. Evaluate generator is your go-to for assessing how well your model performs on a dataset that isn't easily loaded into memory all at once in massive datasets. It calculates the loss, giving you an idea of the model's accuracy. On the other hand, predict generator generates predictions based on a sequence of data from your generator. This is fantastic for things like generating captions or simulating future events. The big difference? Evaluate generator tells you about the asterisk loss asterisk, while predict generator gives you the actual asterisk predictions asterisk. A quick reminder: make sure that the batches your generator yields are compatible with your model's expected input shape. Okay, let's talk about masking in Keras sequence models. Imagine you're working with text data sentences of different lengths, right? When we need to feed this into a recurrent neural network like an LSTM or GRU, we often pad the shorter sequences to match the longest one. But that padding can cause problems. It's essentially noise in the model. Masking is a clever solution. It tells the model which parts of the input are actually meaningful and which are just padding. We use a Boolean mask: true for valid data, false for padding, and the model learns to ignore those padded areas during training. This leads to much better results, especially when using attention mechanisms like you'd find in transformers. Okay, let's dive into implementing RNN, LSTMs, and GRU in Keras. First up, we have the basic RNN. It's the foundational building block, processing sequences one step at a time and maintaining a hidden state. Then we move to LSTMs, which are fantastic for tackling longer sequences because they can remember information over extended periods. They use gates to control the flow of data through the cell state. Finally, GRU offer a streamlined alternative to LSTMs. They are simpler but often perform just as well. When using an LSTM, it's important to set return sequences equals true if you need to process sequences with varying lengths. Remember that the choice between LSTM and GRU depends on your specific data and task. Experiment to see what works best. Let's talk about embedding layers. They're super important when dealing with text or any categorical data. Essentially, an embedding layer takes discrete values like words in a sentence and transforms them into dense vectors. These vectors capture the relationships between those elements. For example, king will have a vector that is closer to queen than it is to table. One hot encoding can become incredibly large and inefficient, but embeddings provide a much more compact way of representing data while still retaining valuable information. They're learned during training. The model figures out what those vectors should look like based on how they're used in the surrounding text or data. Okay, let's talk about building your own training loops in Keras. Sometimes the built-in tools aren't quite enough. Maybe you're dealing with a complex data pipeline or need to implement something really specific like curriculum learning. The core idea is that you take control of everything: loading your data, defining your loss function, which could be anything, and choosing an optimizer. Essentially, you create the training step function, which handles the forward pass through your model, calculates the loss, computes gradients, and then updates the weights using your chosen optimizer. Think of it as building a mini framework around Keras' core component. Okay, let's talk about model subclassing in Keras. It's a really powerful technique for advanced users. Basically, you create your own custom layers by inheriting from the base layer class. You then define what your layer asterisk does asterisk inside the init method, setting up things like weights and biases. The crucial part is overriding the call method. This is where you actually implement how your layer processes an input and generates its output. Sometimes, you might also need the build method if you want your layers to adapt dynamically based on the shape of their inputs. It gives you a lot of control and lets you create truly specialized models. Think of it as building blocks that go beyond the standard Keras layers. Okay, let's talk about input shapes in Keras. Think of it like this: your model is hungry for data. The input shape tells the network exactly what kind of data you're feeding it. How many rows and columns are we talking about? For images, that's usually height and width. You specify this when creating your input layer or within a sequential model using the input layer. It's really important to get right so the network can learn effectively. It dictates what information it expects at the beginning. Okay, let's talk about keeping an eye on how your Keras model is learning. Monitoring and logging metrics during training is a really important step. First, you can easily specify the metrics you want to track, like accuracy or loss, directly in the model fit function using the metrics argument. It automatically logs those for you. Alternatively, you can use callbacks, which are like little helpers that run during training. The TensorFlow callback tensor board is super popular because it lets you visualize your metrics in real time. Or, if you want even more control, you can create your own custom callback to log specific information or save it to a file. Okay, let's talk about model summary in Keras. Think of it like getting a quick architectural diagram of your model. It's a really helpful tool for understanding exactly what layers are inside your network, how data flows through them, and the size of each layer, specifically the number of parameters that need to be learned. It lists all the layers, shows you the shape of the output from each one, and importantly, it gives you the total number of trainable weights in the whole model. So, if you're preparing for an interview, knowing how to interpret this summary is a must. Let's talk about saving and loading models in Keras. It's super important to be able to reuse your trained models later, or deploy them somewhere else. Keras makes this really easy with the model save function. It essentially creates a snapshot of everything about your model, its structure, all those learned weights, even how the optimization process was set up. This snapshot gets saved as an H5 file, which is a common format. When you need to use that model again, use Keras models load model to read it back in. It's like restoring your model from a backup. Just be mindful of the file format and make sure the version you're loading is compatible with the one you saved. Let's talk about how to really make the most of Keras. You've likely heard of both the functional and sequential API. They're fantastic for building neural networks. The sequential API is super easy for creating straightforward, linear models where you just stack layers one after another. But what if your network gets a bit more complex? That's where the functional API comes in. It lets you build models using dictionaries of functions, giving you amazing flexibility to connect layers in all sorts of ways. The really cool part is that you can actually combine these two approaches. You might start with a sequential model for an initial section of your network and then use the functional API to weave it together with other pre-built components or even different sequential models. It's a powerful way to build sophisticated architectures, and this example shows how you can do it. Okay, so let's tackle hyperparameter optimization. It's a really important part of getting the most out of your Keras models. Keras Tuner is like a super smart assistant that takes care of finding the best settings for your model. Basically, you tell it what metric you want to improve, like accuracy or loss, and then which specific settings, hyperparameters you want it to adjust, such as learning rate or batch size. It then intelligently explores all those combinations automatically, using clever techniques like Bayesian optimization, and returns the best results. It handles all of the work so that you can focus on building great models. Let's talk about callbacks in Keras. They are like little helpers that run during your model training process. You create a custom class, inheriting from the callback base class, and then define specific methods, like on epoch begin or on batch end. These are where you put in your own logic, whether it's printing progress updates, saving checkpoints, or adjusting things like learning rates. It's really about adding custom behavior to what Keras is doing automatically. Okay, let's talk about the difference between these two common Keras functions. Both model fit and model fit generator are used for training your neural network. However, they handle data differently. If you have a dataset that can easily fit into your computer's memory, then model fit is probably the easiest option. You just feed it your entire dataset as NumPy arrays. But what if your dataset is massive asterisk? That's where model fit generator comes in. It's specifically designed for those huge datasets that won't fit into memory all at once. Instead of feeding everything up front, fit generator uses a function called a data generator. This generator creates batches of data on the fly as you train. It's like simulating a stream of data. So basically, fit takes the whole thing, while Fit Generator builds it piece by piece. It's much more memory efficient when dealing with large datasets and gives you control over batch sizes too. Okay, let's talk about model ensembling in Keras. Ensembling is a really powerful technique. It's like getting several experts to tackle the same problem together and then combining their insights for a better overall solution. There are a few different ways you can go about this in Keras. First, there's simple model averaging, where you just take the average of each model's predictions. Then you have weighted averaging, which lets you give more importance to models that perform particularly well on your validation data. You could train 3 different CNN and then average the predictions. It's a quick way to potentially boost accuracy. Or, for more sophistication, you can use stacking, where you train a separate meta-learner model to actually learn **** to best combine the outputs of your base models. It's like having a master strategist decide which models are most valuable and how to weight them accordingly. Okay, let's talk about something that can really speed up your Keras models. Mixed precision training. The core idea is to use both 32-bit and 16-bit floating point numbers during the process. This might sound complicated, but it actually has some huge advantages. First off, you'll be using less memory, which means you can train bigger models on GPU that might not have enough space otherwise. Also, operations with 16-bit data are often much faster, especially if your GPU has tensor cores. And because of the reduced memory footprint, you can also use larger batch sizes, which generally leads to better and more consistent training. Sometimes it even helps prevent some tricky numerical problems that can pop up when using 32-bit floating point numbers. Okay, let's talk about visualizing how your Keras model is doing. It's super important to keep an eye on both the training loss and accuracy *** and the validation loss and accuracy. The validation data argument in the model fit function lets you feed data from a separate set to your validation set during training, so you can see how well your model generalizes to unseen data. Alternatively, using callbacks like early stopping or model checkpoint configured to log metrics to TensorBoard gives you a really powerful interactive visualization of those metrics over time. Think of it as a dashboard for your model's learning process. It helps you spot if it's starting to memorize the training data overfitting or not learning enough underfitting. Okay, let's talk about how we track our models during training. Keras makes this really easy. You can log all sorts of data using the model fit method. The key is to use callback things like early stopping and model checkpoint that capture information as your model learns. Keras automatically returns a history object, which is basically a snapshot of everything that happened during training. This object contains metrics like loss and accuracy both for the training data and often for validation data too. You can easily access these metrics using the keys in the history dictionary. Just print them out to see what's going on. It's super helpful to save your model *** and * the history so you can analyze how it performed. Okay, let's talk about early stopping in Keras. It's like having a built-in stop training button. It prevents your model from overlearning the training data and performing poorly on new data. The key part to understand is the patience parameter. By default, Keras waits 3 epochs without seeing an improvement in validation loss before stopping training. If you increase the patience value, it'll wait longer, giving your model more time to learn potentially. But be careful, too much patience can lead to overfitting. Conversely, reducing patience means the model stops earlier, which might be good if you suspect it's already overfitting. Let's talk about categorical accuracy in Keras. It's a really important metric when you're dealing with multi-class classification problems, basically situations where you have more than 2 categories to predict. Unlike simple accuracy, which just looks at how often your model gets the overall right answer, categorical accuracy digs deeper. It checks if the model is correctly identifying which specific category each sample belongs to. It compares the probability distribution the model outputs for all classes against the true one-hot encoded label for that sample. Think of it like saying, did the model correctly identify this sample as belonging to class 2 and nothing else? It's a more nuanced way to evaluate performance when you have several possible outcomes. Understanding the difference between categorical accuracy and standard accuracy is really key to interpreting your model's results. Okay, let's talk about time-distributed layers. They're like specialized processing units for your sequential data. Essentially, they apply a specific function to each element within your sequence. Think of it as treating each piece individually. They are built on top of another layer, and they shine when you need different treatments at different parts of the input. This is especially useful in sequence-to-sequence tasks like translation or summarization, and when dealing with sequences that have variable lengths. You could use them to apply different transformations like different activation functions to each element, giving you more control over how information is processed. Okay, let's talk about gradient clipping. Imagine you're training a really complex neural network. It can get wild. Sometimes the gradients which tell the model how to adjust its weights become huge, like really huge. This is called exploding gradients, and it's a big problem because it can make training unstable or even stop entirely. Gradient clipping is basically a safety net. Keras makes it easy by letting you control how large those gradients can get using the clip norm or clip value arguments in your optimizer, like ADAM or RMSprop. Clip norm clips based on the magnitude of the gradient, while clip value caps individual gradients at a specific value. It's a simple but incredibly effective way to keep training smooth and robust. Okay, let's talk about padding in Keras for NLP. Think of it like this: you're working with text data, and each piece of text, like a sentence or paragraph, has a different length. Deep learning models need consistent input sizes, so we use padding. We add special tokens, often just zeros, to the shorter text to make them all the same length as the longest one in your dataset. It's essential for efficient batch processing and avoiding errors. Keras provides a handy function called pad sequences that handles this seamlessly. You can tell it exactly where to put the padding at the beginning or end of each sequence, making sure everything is ready for your model. Okay, so let's dive into masking layers. They are super useful when you're working with sequence models like LSTMs and GRU. Basically, a masking layer is like a little flag that tells your model, hey, ignore this part. It works by creating a binary mask, ones for the good stuff and zeros for padding. Padding is often added to make all sequences the same length when you're batching them up. But if your model sees these zeros, it can learn and correct patterns based on that padding. Masking removes those zero padding errors, resulting in more accurate results and better overall performance. Okay, so let's say you've built a really cool Keras model and it's performing great. But maybe you want to reuse some of its learned knowledge in a different project, like using it as the foundation for something new. Or perhaps only certain parts of your model are useful for your current task. That's where saving just the weights comes in handy. You can use model get weights to extract all the weights from the model, and then you can easily save each weight tensor individually. This is super helpful when dealing with transfer learning or customizing models by selectively incorporating parts of an existing network. The code snippet shows how to iterate through the list of weights and print their shape and data type, a good way to verify you've retrieved the correct values. Okay, so let's talk about saving your Keras models. You'll often be asked how save weight and save differ. The key thing to remember is that save weight specifically saves the learned weights as numbers that represent what your model has learned during training. It doesn't include the model structure itself. On the other hand, save will save the entire model, its architecture, the way it's built, all those learned weights. So if you want to easily reload and use a model later without needing the original source code, save is your go-to. It's like sending just the notes versus sending the whole textbook. Okay, so let's say you've spent a good chunk of time training your Keras model. You want to continue it later, or maybe on a different machine. That's where saving and loading weights comes in. The key functions are save weights and load weights. Save weights takes the weights from your model and saves them to a file like an H5 file. Then load weights does the reverse. It loads those saved weights back into a new Keras model that has the exact same architecture as before. To resume training, you'll create a new model with the identical layers and setup, load the weights from your save file, and then just start fitting it again. a little bit like picking up where you left off. Just remember to make sure you're loading the weights into a model that has the same structure as the one you were originally training. Okay, let's talk about model checkpoints. Basically, they're like saving points in your Keras training process. If something goes wrong, hardware failure, a bug, or you just want to try something different, you don't have to start from scratch. Checkpoints store the current state of your model, including all its weights and architecture. It's super useful for preventing lost progress and makes experimentation much easier because you can always go back to a previous point. To configure them in Keras, you use the model checkpoint callback, passing it a path where you want to save the checkpoints and how often, usually every epoch. You'll also want to consider whether to only save the best performing model based on your validation set. Let's talk about how we make sure our Keras models aren't just doing well on the training data but actually generalizing to new, unseen data. That's where cross-validation comes in. The most common approach is k-fold cross-validation. Think of splitting your dataset into k-groups or folds. Then, you train your model on all but one fold and use that fold as a separate validation set to see how well it performs. This process repeats k times, with each fold acting as the validation set once. Finally, you average the results across all those validations to get an overall performance estimate. Stratified k-fold is especially helpful if you have imbalanced datasets, ensuring that your folds maintain a similar distribution of classes. A simpler alternative is just using a train and validation split, but k-fold offers more robustness. Okay, let's talk about dealing with those tricky imbalanced datasets in Keras. Often, one class will have way fewer examples than another, and that can really mess up your model's performance on the less common classes. The good news is Keras makes it pretty easy to fix this. You can adjust the weight given to each class during training using either the class weight parameter in your model fit call or by assigning individual sample weights. With class weight, you essentially tell Keras, hey, pay more attention to this class, and it does that by giving it a higher weight. You can calculate these weights based on how many samples are in each class, making sure the minority classes get proportionally more importance. Don't just pick random numbers though. Experiment with different values to find what works best for your specific data. Okay, let's talk about some drawbacks of using Keras sequential API when you're building your deep learning models. The main thing is that it's really good for simple, straightforward architectures like a basic feed-forward network. But if you start getting into anything more complicated, things get tricky pretty quickly. You have limited control over how layers are connected, and creating branching paths or even sharing weights between different parts of your model becomes incredibly difficult. It's also tough to build advanced architectures like ResNets or Inception nets with just the sequential API. You'd essentially be copying and pasting layers manually, which is a recipe for errors. If you need more flexibility, then definitely explore the functional API or even subclassing techniques. Okay, let's talk about model subclassing in Keras. It's a really powerful technique that lets you build truly customized models. Basically, it means inheriting from the base Keras layer in Keras model classes. Think of it as creating your own building blocks for neural networks. You would use this when you need a layer that doesn't exist out of the box. Maybe you want to incorporate data from an external source, or you have a very specific calculation you need to perform. It's also great for designing completely new model architectures by building on existing layers but adding your own custom connections and behaviors. Just remember to make sure you're implementing the call method correctly and handling all of Keras' tracking features. Okay, let's talk about eager execution in Keras and TensorFlow. For a long time, TensorFlow operated on a graph-first principle. You'd build the entire computation plan before actually running it. Think of it like building a factory before starting to produce anything. Eager execution is different. It's like doing things as you go. Essentially, operations are executed immediately when called, just like in standard Python. This makes debugging much easier because you can see what's happening at each step. It also feels more natural for programmers used to writing code that executes right away. The biggest advantage is that it allows for dynamic graphs, meaning your models can be flexible and adapt based on conditions or even handle sequences of varying lengths, which is really powerful. Let's talk about visualizing your Keras training with TensorBoard. It's an incredibly helpful feature. TensorBoard lets you really get a sense of what's happening inside your model, from seeing how the loss is decreasing to understanding the data flowing through each layer. To use it, you first make sure TensorFlow and Keras are set up. Then, you create a summary writer to store all the information. Inside your training loop, you'll use functions like TF, summary, scalar, which logs things like loss or accuracy, and other similar tools to track different aspects of your process. Finally, just type TensorBoard logdo in your terminal to launch TensorBoard and see all the beautiful visualizations. Okay, let's talk about lambda layers in Keras. Basically, a lambda layer is just a function you create that you then wrap inside the lambda layer in Keras. It's super useful when you want to add custom logic or operations into your neural network without having to build your own separate layer from scratch. You could use it for things like creating your own activation functions, manipulating data before it goes into the model, or even adding some debugging tools. Think of it as a way to inject specific calculations directly into your model's flow. Okay, so after you've trained your Keras model and it's performing really well, the next big step is getting it out to users. That's where TensorFlow serving comes in. Basically, it's a server that takes your saved Keras model, typically stored as a saved model, and makes it accessible via an HTTP endpoint. You first export your model using standard Keras methods. Then you set up TensorFlow serving, which is a bit of a separate installation, but the documentation is great. After that, you load the saved model into serving with a special function. Finally, you can send prediction requests to the server and get results back. You can use tools like curl or Python's requests library to do this. It handles all the behind-the-scenes scaling and monitoring, so you don't have to worry about it. Okay, let's talk about how Keras models make predictions. Both predict and predict classes are used for getting results, but they give you slightly different information. Predict returns a whole bunch of numbers, probabilities for each possible outcome, really. It's great when you need to see the likelihood of something happening. Think about predicting house prices. It will give you a score for each price. On the other hand, predict classes just tells you asterisk which asterisk class was predicted. It's perfect if you only care about the category or label, like classifying an image as cat or dog. Essentially, predict gives probabilities, and predict classes gives you the class labels directly. Let's talk about creating custom optimizers in Keras. It's a really powerful way to fine-tune your neural network training. First, you inherit from the base Keras optimizer class, which gives you all the necessary tools. Then you define the initialization parameters for your optimizer, like maybe a learning rate schedule. The heart of it is the getUpdates method. This is where you actually calculate how to update the model's weights based on the gradients in your optimizer's internal state. This method returns a list of operations that Keras can apply. Finally, you might need to implement compute gradients if you want to compute gradients from scratch. It's a relatively involved process, but gives you incredible flexibility in controlling how your model learned. Let's talk about learning rate decay schedules. They are a really useful tool when training your Keras models. Think of it like this: starting with a big push can get you moving quickly, but as you get closer to the goal, you need finer adjustments. A fixed learning rate might overshoot and bounce around without ever settling down. Decay schedules automatically reduce the learning rate over time, encouraging more stable convergence. Keras provides handy tools for creating these schedules, like exponential decay, where the rate decreases by a factor each epoch, or polynomial decay, which follows a curve. You can also use step decay to reset the learning rate after a certain number of epochs. Just remember to apply this schedule to your optimizer ADAM and RN proper common choices. Okay, let's talk about how Keras helps you build image classification models. It all starts with getting your images ready. Resizing them to a consistent size is crucial. Then you'll build a CNN, which typically involves convolutional layers to extract features, pooling layers for efficiency and robustness, and finally, fully connected layers to make the final prediction. Don't forget to choose an appropriate optimizer and loss function based on the type of classification you're doing. It's really about learning how these layers work together to automatically learn the best features from your image. Is a great area for experimentation. Okay, so let's talk about global average pooling toward D. It's a really important layer to understand when you're working with Keras and image data. Think of it as a way to condense information from your convolutional layers. It takes the output of those layers and calculates an average activation for each feature map. Essentially, it gives you one number per filter that represents how active that filter was across the entire image. This dramatically reduces the size of your model and makes it more robust to small changes in where features are located within the input, which is really handy when you're building a classifier. Okay, let's talk about separable conv2D. It's a clever optimization used in Keras. Think of it as a smarter way to do convolution compared to the standard conv2D layer. Conv2D does one big job. It slides filters across your data and calculates dot products. Separable conv2D breaks this down into two smaller, more efficient steps. First, we have depthwise convolution, which processes each channel independently, like having a separate filter for each color in an image. Then, we use a pointwise convolution or Wonksian convolution to combine those channels and create the final feature maps. The result? Significantly fewer parameters and faster computations, especially when you're working with larger datasets or complex images. Let's talk about multi-output models in Keras. They're fantastic when you need a model to predict several things at once. Essentially, you define separate output layers for each prediction you want. You use the model output method for each of these, and Keras intelligently bundles them into a list. You can then access those individual outputs after your model is trained. It's a really clean way to handle complex tasks. Okay, let's tackle this Keras question. It's easy to get these terms mixed up. An activation asterisk layer asterisk is just a placeholder. It's like saying I want an activation. It's part of the architecture and sits after other layers. Now, an asterisk activation function asterisk is actually the math itself. It's the specific formula that gets applied, like ReLU or sigmoid. So, the layer asterisk uses asterisk an activation function to add nonlinearity. Think of it as the layer being the container, and the function being what's inside. Okay, let's talk about handling variable length sequences in Keras. Essentially, when you're working with data like text or time series where each piece of information isn't always the same size, things get tricky. Keras provides two key tools, padding and masking. Padding involves adding special tokens, usually zeros, to make all your sequences the same length. Think of it like lining up different size blocks so they're all the same height. The pad sequences function does this for you. And crucially, we also use masking. Masking tells the model which parts of the sequence are asterisk real asterisk data and which ones are just padding. This prevents the model from being influenced by this filler tokens, a really important detail for accurate training. Does that make sense? Let's talk about bidirectional wrappers in Keras. They are a really neat way to handle sequences of data where the order matters, and understanding both past and future context is key. Think of it like reading a sentence. You don't just read from left to right, you understand it better by considering what came before asterisk and asterisk what comes after. A bidirectional wrapper combines two recurrent layers, one that processes the sequence forward and another that does it backward. The hidden states from both are then combined, usually through concatenation or averaging. You typically use them when context is crucial, like in sentiment analysis to understand how words relate to each other across a sentence, or for NER tasks where identifying entities benefits from considering surrounding words, or even in time series forecasting where past values influence future predictions. Okay, let's talk about using pre-trained models with Keras applications. These are incredibly helpful because they've already been trained on huge datasets like ImageNet, meaning you don't have to train a model from scratch. There are several popular choices, including VGG16 and VG19, ResNet 50 and ResNet 101, Inception v3, and MobileNet. The key here is that you load the pre-trained weights using the weights parameter, and you often don't need the final classification layer, so we can set include top equals false if we're just using it as a feature extractor. Okay, so transfer learning is a fantastic way to boost your model's performance, especially when you have limited data. Now let's talk about the two main ways we can use pre-trained models: fine-tuning and feature extraction. Feature extraction is like saying, here's an amazing feature extractor, but I don't want it to change its knowledge. You freeze all the layers of that model and just use its output as features for a new classifier you build yourself. It's simpler and faster. On the other hand, fine-tuning is when we let the pre-trained model actually learn asterisk with asterisk our data. We unfreeze some or all of the layers and train them along with our new classifier. This can lead to even better results if done right, but it needs a bit more care and resources. Okay, so let's talk about getting your Keras models to leverage multiple GPU. It's a huge performance booster for big datasets and complex networks. The key is using the multi-GPU executor, which comes built into Keras through TensorFlow distribution. You have a few strategies you can choose from, like mirrored strategy, where each GPU gets its own copy of the model, or central dispatcher strategy if your layers are independent. Wrapping your model with the strategy ensures it runs efficiently across all available GPU. And don't forget, make sure your GPU have enough memory to handle everything. Mixed precision training can also help with that. Okay, let's talk about how we check if our Keras models are doing a good job. We have two main ways to evaluate them: model evaluate and model test on batch. Model evaluate is your friend when you're training. It lets you see how the model is learning in real time, showing you things like loss and accuracy as it goes. It just gives you those numbers for metrics and losses. But if you want to know really how well your model will perform on data it's never seen before, that's where model test on batch comes in. This method takes a batch of test data and returns the predictions your model makes on that batch. It also gives you those same loss and metric numbers. The key takeaway is this: use evaluate to monitor during training, but for a final unbiased assessment of how your model performs, go with test on batch. Okay, let's talk about how to save your custom Keras layers and objects, basically making sure they stick around for later. The key is serialization. First, you need to make sure your custom layer or object can be easily described. This means implementing two special methods: getConfig and fromConfig. getConfig essentially tells Keras what the layer needs, like its number of units, and fromConfig is the reverse, taking a description and recreating the layer from it. Then, you can use Keras save function to serialize your whole model, including those custom pieces. Finally, to load them back later, you'll either use load from config for just the layer, or load model if you want the entire thing. Okay, let's talk about attention mechanisms. They're a really clever way to boost your neural networks. Essentially, instead of treating all input data equally, attention allows the model to prioritize what's most important. It's like you're reading a sentence and naturally focusing on certain words more than others. In Keras, we use the attention layer, which calculates how relevant each part of the input is to the current output. We define query keys and values, compute attention weights based on their similarity, and then create a context vector that summarizes the focused information. You'll find this implemented using layers like dense for scaling and combining the key information. Okay, let's talk batch normalization. It's a really handy tool in Keras that can significantly boost your neural network training. Basically, it normalizes the activations of each layer, it subtracts the mean and divides by the standard deviation within each mini batch. Then, it learns some scaling and shifting parameters to adjust the distribution. Why is this useful? Well, it helps combat vanishing and exploding gradients, letting you use higher learning rates and training faster. Plus, it can often lead to better overall generalization of your model, meaning it performs better on data it hasn't seen before. You'll commonly see it used after dense layers or convolutional layers. Here's a quick example showing how to add batch normalization into a Keras sequential model. Okay, so when it comes to choosing between Keras, TensorFlow, and PyTorch, there's a good reason why Keras is often recommended for interviews and for many real-world projects. The biggest advantage of using Keras is how much easier it makes building models. It's like a simplified toolkit that lets you quickly prototype ideas and get results without getting lost in the complexities of TensorFlow. However, that simplicity comes with a trade-off. Keras abstracts away some of the lower-level controls. If you need absolute precision or are working on something very specialized, TensorFlow or PyTorch might offer more flexibility. But for most use cases, especially when you're starting out, Keras is an excellent choice. Okay, let's dive into building a text classification model using Keras. First, you'll need to get your data ready. That means breaking it down into smaller pieces like words or tokens, and ensuring everything is the same length. Then, we build a basic architecture, often using something like a text CNN or an LSTM network. I've shown a simple example with an embedding layer followed by an LSTM, and then finally a dense layer to make our prediction. It's essential to train your model on properly prepared data and evaluate its performance after, and accuracy is key. Remember that processing the text correctly can make a huge difference in how well your model performs. Okay, let's talk about building a generative adversarial network or GAN in Keras. It can seem a little complex at first, but we can break it down into manageable steps. First, you need to define both your generator and discriminator networks. The generator takes random noise, essentially a seed of randomness, and tries to turn that into something that looks like an image. You'll use layers like dent and conv transpose for this. Next up is the discriminator. It's like a critic judging whether an image is real or fake. It uses convolutional layers and then flattens the output to feed into a dense layer. Then you compile both models, setting up loss functions and optimizers. The generator tries to fool the discriminator, while the discriminator tries to catch the generator's fakes. You'll need to train them iteratively, adjusting learning rates along the way, and constantly monitoring metrics like loss and image quality to see how things are progressing. Okay, let's talk about label smoothing. It's a clever trick to help your models avoid becoming *to* confident. Normally, when you train a neural network, the loss function gives a big penalty if it gets an answer exactly right. But that can be problematic, especially with messy data or rarer classes. Label smoothing gently nudges the model to think about other possibilities instead of being super sure about its correct prediction. It's like telling the model, okay, you're probably right, but don't completely rule out anything else. We can add a small amount of probability to the incorrect labels and reduce the probability of the true label slightly. This helps create a more robust and less overconfident model. You implement it using Keras' categorical cross-entropy loss function. Just adding a smoothing parameter value like 0.1 is common. Okay, let's talk about embedding regularizers. These are essentially penalties we add to our model's training process, specifically designed to keep those word or category representations, what we call embeddings, from getting too big and wild. It's like saying, hey model, don't create gigantic vectors for your words, stay relatively compact. This helps prevent overfitting, especially when you have a lot of different categories or words, keeping things nice and stable. Okay, let's talk about making your Keras models run faster and more efficiently. Profiling is the first step. It's like a diagnostic tool that pinpoints exactly where your model is spending most of its time. Tools like Keras Tuner, TensorBoard's Profiler, or TensorFlow's built-in profiler can show you how much time is spent on each layer and operation. Once you know the bottlenecks, you can start optimizing. This could mean simplifying the model by reducing layers or filter sizes, experimenting with different batch sizes to find the sweet spot for your hardware, making sure your data loading is as fast as possible, maybe using generators to avoid memory issues, and even exploring more efficient layer designs. Okay, let's talk about transfer learning with Keras, and specifically using the Inception v3 model. It's a fantastic way to get started on projects where you might not have tons of labeled data. First, you load up a pre-trained Inception v3. This is a really smart move because it already knows how to recognize a huge variety of visual features thanks to its training on ImageNet. The key here is that we're going to freeze most of the layers in that model. We don't want them to change. We keep those weights fixed, preserving all the knowledge they have. Then, we add our own custom layer, typically a dense layer or a few right at the top. This new layer will be responsible for learning how to classify your specific dataset. Finally, you just train only that newly added layer. The Inception v3 part acts like a super smart feature extractor, providing those rich visual representations, and it's doing all the heavy lifting in terms of recognizing patterns. Okay, let's talk about building attention-based sequence-to-sequence models with Keras. The key here is understanding that these models aren't just processing the sequences, they are actively deciding what to focus their attention when generating the output. We have an encoder which takes our input sequence and creates a context vector, a decoder which builds the output, and then this really clever attention mechanism. It lets the decoder dynamically shift its focus to different parts of the input as it generates each part of the output. The code snippet here shows a highly simplified example using Keras' built-in attention layer. You'll need to adapt it to your specific dataset and model architecture, usually incorporating LSTMs or GRU for better results. Let's talk about convolutional layers in Keras. Think of them as convolutional filters specifically built for processing data that's arranged in a single dimension, like a sequence. They're really handy when you're dealing with things like time series. Imagine predicting stock prices based on past trends, or even analyzing text where each word is a distinct element. Essentially, they help you find patterns and features within those sequences. You'd use them when your data has an inherent order or temporal relationship. If it's just spatial information like in an image, then convolutional might be a better fit. Okay, let's talk about stateful RNN in Keras. These are a bit different from regular RNN. They have memory. Instead of treating each input as completely separate, they carry information forward over time. This is super useful for things like translating languages or understanding speech, where the context of what came before really matters. However, there's a catch. Because they maintain this hidden state, you need to be careful not to let information from one sequence bleed into another unintentionally. It's called memory leakage and can mess up your results. And initialization is key too. How you start the network's memory will affect its performance. Thank you for watching.